In this lesson we will look at A-level chemistry paper 2 from AQA from June 2018. So there are 11 questions, you get 2 hours, so if you give yourself 10 minutes per question you should be fine and have some time to go over everything again. Okay, so let's start with question 1. It's about reactions of alkanes. And it says alkanes can be used as fuels, and you're supposed to give an equation for the combustion of heptane in an excess of oxygen. So when you hear excess of oxygen, it's complete combustion. If it's not an excess of oxygen, it's incomplete combustion. But in this case we have enough oxygen, so the only products will be CO2 and H2O. And we are starting from heptane, so that's C7H16, and it's with oxygen, so O2. Okay, now we just need to balance the equation. So on the left hand side we have 7 carbons, so we need 7 carbons on the right hand side as well. On the left hand side we have 16 hydrogens, so we need to put 8 here to make 16 hydrogens on the right hand side, and this will just give us a total number of oxygen is 14 plus 8, so that's 22, so that means we stick 11 here. Okay, so that was easy question for 1 mark. The next one is heptane can be obtained from the catalytic cracking of hexadecane C16H34 at a high temperature. You're supposed to identify a suitable catalyst for this process and give one condition other than a high temperature for this reaction, and you're supposed to give an equation for the catalytic cracking of this molecule. So what can be suitable catalyst for this process? Well, it can be either zeolite, or you can also say silicon oxide, I would say. And there are a couple more that you could use, like aluminum oxide and others. Okay, give one condition other than high temperature, so this can be, high temperature, high pressure, so I would say increased pressure. And you're also supposed to give an equation for the catalytic cracking of one molecule of hexadecane, so that's C16H34. To produce one molecule of heptane, so we're cracking this and into heptane. Heptane is C7H16. One molecule of cyclohexane. Cyclohexane looks like this. So there are 6 carbons in a ring, and each carbon has 2 hydrogen atoms. I'm not going to draw them all, but the formula is C6H12. And also one other product. Okay, we'll figure out what the other product is. And to figure that out, let me just remove that. We're gonna write down what is on left hand side and what is on the right hand side. So on the left hand side we have 16 carbons and 34 hydrogens. So on the right hand side we have 13 carbons, 7 from the heptane and 6 from the cyclohexane. And how many hydrogens do we have? We have 28 hydrogen atoms. So this means that we are missing 3 carbons on the right, and we are missing 6 hydrogens on the right hand side. So really what is going to be the we just need to remove this. The missing compound is going to be C3H6. So now we balance the left hand side and right hand side. Okay, so 3 marks for that, for each line. Next part, alkanes can be used in free radical substitution reactions to produce halogenoalkanes. Give an equation for the propagation step in the reaction of butane to form 2-chlorobutane. Okay, so you know that it's chlorine there, so that's going to be the radical. In general, the initiation step is Cl2 needs UV light to break this Cl-Cl bond homolytically, which means that each chlorine atom will take one electron, so generating 2 chlorine radicals. So from the initiation step, we got 2 chlorine radicals. So we're gonna take one and react it with the butane. So that's butane looks like this. So there is CH3, CH2, CH2, CH3. And now we need to generate 2 chlorobutane, so we're going to take the hydrogen from the second carbon, whatever end you want to take it from, CH3CH, so this is going to be radical on this second carbon, CH2CH3, and we're going to generate also HCl. And now we have the second radical here, CH3CH, CH2CH3, and I'm going to react it with CO2 because there are a lot of CO2 molecules around, and we regenerate the chlorine radical, which acts as a catalyst, so this reaction can go over and over again. And we also create the 2-chlorobutane as said in the question, so CH3, CClH, CH2, CH3. Okay, so in this question, just make sure that you don't forget the on which carbon it is formed, the radical, and just make sure everything is nice and balanced. Okay, so next question is about CFCs. So chlorofluorocarbons are a group of halogenoalkanes currently banned in many countries. They cannot be used as solvents or refrigerants because of their effect on the environment. And the structure of CFC is shown here, and so there are chlorine carbon bonds and fluorine carbon bonds, and you're supposed to identify the radical produced from this CFC that is responsible for the depletion of ozone in the atmosphere. Okay, so this is basically the same thing as we've done before. We obviously say that it's chlorine radical that is responsible for that, and there are chlorine radicals in here. So really what's happening is that the UV light breaks one of these carbon chlorine bonds, and then homolytically, and then there are 2 radicals generated, and one of them is chlorine radical. And explain with the aid of equations why a single radical can cause decomposition of many molecules of ozone. Well, we partially explained it in the question before when we said that the chlorine radical is regenerated. So, but in this question is about ozone. So let's do the reaction with ozone. We have chlorine radical with ozone, and we produce ClO radical and oxygen. And then there's the first step of the propagation, and then ClO radical reacts with another molecule of ozone and recreating the Cl radical just like in the equation in the question before, and another 2 oxygen molecules. Okay, so firstly, why a single radical can cause decomposition? Well, because the Cl radical is regenerated. So that means that a chain reaction of the O3 decomposition is taking place. And another thing to notice is that the overall equation for this, or the overall reaction, is that Cl radical is regenerated, ClO radical is just some intermediate, so really we are starting with O3 from both equations, so 2O3, and we go to 3 O2 molecules. So that's the overall equation of the ozone decomposition for this reaction. Okay, you get 4 marks for this, which is quite generous. So 1 for the radical, I think you 2 for the for both of these reactions, and then for the reasoning. Okay, let's get to the next one. So this one is about halogenoalkanes. This one is about halogenoalkanes. It says they are useful compounds in synthesis, and the reaction pathway is shown. Okay, so yes, firstly, let's just not look at the equations first because we don't need to understand it right now. Let's go get some marks. So we're supposed to give the UPEG name for the CH2OH, CH3, CH2Br. Let's first draw what this molecule actually looks like. So we get CH2OH, and then we have CH3. When it's in brackets, it means that it's substituent. And then we have CH2Br. And you're supposed to give the UPEG name. So in this case, they're trying to figure out if you know what is the priority of these substituents. So there is OH, there is CH3, and there is Br. So which way are we gonna label or number the carbon chain, the longest carbon chain, which in this case are the 3 carbons? Well, obviously oxygen is going to have the highest priority right now, so there's going to be 1, 2, 3, like that. So from this we know the longest chain is propane, so it's going to be something like propane. It's alcohol, so 1 O, because O is the ending for alcohols, and then we have 2 methyl, and then we have also 3 bromo. So 3 bromo, 2 methyl, propane, 1 ol. And obviously you need to get this one right and this one right, so they know that you numbered the carbon chain correctly. This 2 here is not actually really necessary, and if you omit that, I don't think you will lose marks, because if you have only 3 carbons, the methyl can be only on 1 of the carbons if the 2 other places are used up for other substitutions. So the next question is, reaction 1 occurs via nucleophilic substitution mechanism, and you're supposed to explain why the halogenoalkane is attacked by the nucleophile in this reaction. So reaction 1 is this one, so there is some base, and we're making alcohol from halogenoalkane. No, there's alcohol as well, but there is a bromine here. So, why the halogenoalkane is attacked by the nucleophile in this reaction? Well, we already draw the molecule here, so I'm going to use that. You know that bromine is much more electronegative than carbon, and the difference in the electronegativities between these 2 elements will cause that bromine will pull the electrons from the bond towards itself, making it partially negative, while the carbon leaves partially positive. And that's the whole idea about this, is that then this carbon here can be attacked by nucleophile because it is a lower electron density than it would be without the bromine. So the reasoning behind this is that bromine is more electronegative than carbon. So carbon becomes partially positive and bromine partially negative. And then, so that's probably for 2 marks here. You need to say that it's more electronegative, and then you need to say that there are partial charges there. So that's 2 marks. We're still missing 1, and I guess that's from the fact that we're supposed to say what will happen actually when it's attacked by the nucleophile. And the answer is that lone pair of electrons can be donated to the partially positive carbon by the nucleophile. Okay, so that's 3 marks there. And let's get to another question. Okay, in this part, they're telling you that the infrared spectrum of compound Y shows a significant absorption in the range 1680 to 1750 centimeters, reciprocal centimeters. So you're supposed to draw the display formula of compound Y. Okay, so let's look at compound Y, because I forgot how it looks. So it says it's C4H6O2. So let's just draw that first. So C4H6O2. Okay, so this range, you just have to literally look at your formula sheet where you have all the IR absorption listed, and you will find out that this is absorption for aldehydes or carbonyls. Can't remember how they put it there. So definitely this was going to be aldehydes. So you're starting with alcohol basically. So if you redraw the chain, the carbon chain that we had before, I'm going to put the carbon on the same place as before. So what did we have was something like this. And that's what we started with. So that was the first compound, and then reaction 1 happened, and literally the only difference is that this bromine was replaced by OH. So let's replace the bromine with OH. And then you know that this is aldehyde, so we're just gonna change these to an aldehyde. And that's it for 1 mark. You just need to recognize aldehyde and then recognize that it is the oxygens at the end. Okay, and there's a compound Z has the empirical formula C3H4NO. And you're supposed to give the structure of compound Z. Now don't forget that the empirical formula doesn't mean that you know exactly the number of atoms in that of the elements in a molecule. So probably there is more than 3 carbons, more than 4 hydrogens, more than 1 nitrogen and 1 oxygen. But we know that this C3H4NO is the simplest whole number ratio of the atoms in a molecule. Okay, so really let's start with what we know, that there probably will be the same carbon chain, and then that there are going to be some substitutions at the end of this. Okay, at this point we have 4 carbons already, so what I would suggest is to try, when they tell empirical formula, it probably always never means that it's going to be just one of these. So if we multiply C3H4NO by 2, we get C6H8 and 2O2, which sounds a bit more reasonable because there are 2 oxygens there as well from the molecule above. So what I would suggest is look at these, look at the compound, and then ask yourself what type of functional group can we have there. So if there is nitrogen, it might be amine, but in this case it's probably going to be nitrile because we have more carbons there. So it would be logical to add the CNs here. So in which case we have 1, 2, 3, 4, 5, 6 carbons now. So that's right, we have 2 nitrogens here. So what are we going to do with the oxygens? Well, if we put oxygens like this in, then we're not going to have enough of hydrogens, right? We're going to have 4 hydrogens, but we need 8. So if we make the oxygens into OH group, it makes more sense. And we have the right number of atoms, if the elements in that compound. And if you can't figure out why is it this way, then just try and figure out why or how this reaction happens. So we're starting with carbonyl. And we go to nitrile. And alcohol. I'm just redrawing the molecule here. So somehow we added a CN and somehow the carbonyl became alcohol. Okay, what happened is that we have these lone pairs of electrons here on both carbonyls. So if we add acids, as I'm just going to draw H+, the lone pair of electrons will grab the protons. I'm just going to redraw. So now the oxygen has three bonds, so it's positive. And now we can attack the carbons, because now they're going to be even more electrophilic than before. We can attack them with Cn minus. And both of these will donate lone pair to the carbon here, and the electrons from the CO bonds will go to the oxygen, making the oxygen neutral again and not positive, and we generate this compound here. So we also answered the second part of this question with this, and the question was reagents for reaction 3. So for this reaction, as we said, we're going to need some acids, and we're going to need some Cn minus, so that can come from potassium cyanide most likely, so KCN.